Hello everyone, welcome back. So in the last video we explicitly stated what no signaling principle is and say that we will work out an example in the next one. Alright, so this is what we will do right now. So let's say again, as usual, you have Alice and Bob, and what we would try to prove is that if Alice performs a measurement or not, Bob's probability distribution will not change. Alright, if that is true, then there is no signaling between them, there is no communication between them. Okay, so let's say that they have shared a system. They have a state like this: 1 by square root of 2 0 0 plus 1 1. Okay, you understand, this is AB and this is AB. All right, so if Alice performs a measurement, okay, so they had this shared state, this is an entangled state, and then they go to two corners of the universe, and now Alice performs a local measurement. And if Alice performs a local measurement, and if he does not, does Bob's probability distribution change? We will check that. All right, so now let's check the first case when Alice does not perform a measurement. Does not perform a measurement. Okay, if he does not perform a measurement, then let's say that Bob does a complete measurement in this basis. Bob does a complete measurement in basis B0 and B1. Okay, so this will be one of his collapse states. So now does it change? Does it if Alice does not do anything, then the probability of getting, let's say BI, let's call two of them in a common name, BI. So the probability of getting BI or I, probability of getting I for Bob will be the state BI inner product phi plus AB mod square. Okay, we use a double mod. This is the notation. But what I try to say is that if Alice did not perform any measurement, then phi plus would stay phi plus. It won't change, right? And if Bob performs a measurement, the probability of getting BI would be the inner product between the state and the basis, right? And the mod square will give you the probability. So let's try to calculate that, and let's see what is the number. And this I can be either 0 or 1 here. Okay, so let's check that, and let's write that as BI B, and you can write it as 1 by square root of 2 0 0 AB plus 1 by square root of 2 1 1 AB, and you want to take the mod square of this. Okay, so I just plugged in the value of phi plus. Now if you take the inner product, this is in the B system, so this will be in the second qubit here and here. Okay, then I can explicitly write it down. This is 1 by square root of 2, and this inner product is a number, so I can write it as BI 0 times, so this 0 on A. So this whole thing, this whole thing is a number. So this is a coefficient, and this is this A is just a vector. 0A is one element of the basis of Alice. All right. So now similarly, The second term can be written 1 by square root of 2, and this will be bi inner product 1, and this will be 1b, and you take a mod square. Okay, and now what I can say is that if you remember, if you have a vector like this, a1 0 plus b1 1 mod square, then that would be nothing but a1 square plus b1 square. I mean mod a1 square plus mod b1 square. Correct? Because 0 and 1 is normalized. So you can write that if you remember from your linear algebra part. So I can write this mod square as half times b1 0 mod square. Okay, this is a number, so let me write this notation as this mod square plus half bi 1 mod square. All right, as 0a and I had a typo here. This should be 1 as well. 1a. Okay, so if 0a and 1a are normalized vectors, so I can write their normal like this. Okay, this is correct. So this can be written as bi 0 0 bi, right? This is the definition of mod in Dirac notation. Half, you can write it bi 1 1 bi. Okay, why did I write a capital? Sorry for that. So this should be written as bi. Okay, so this can be written as half bi, and this can be written 0 0 plus 1 1, and this bi again. All right, but this part in the parenthesis, this part is nothing but 1 from the completeness relation. Completeness relation. All right, if this is 1, then the next line is pretty easy. We can write it as half bi bi, but we can assume that bi's are normalized as well. So then the mod square of bi is just 1, then this is nothing but half. All right, so the probability of getting this I is half. So probability of getting b0 is half, the probability of getting b1 is half. Now let's check what happens if Alice performs a measurement. Now if Alice performs a measurement, okay, performs a measurement, okay, so what happens then? Then it will be a probabilistic sum, because when Alice performed a measurement, Bob's qubit collapsed, but Bob doesn't know what it is because they didn't communicate, right? So probability of getting I for Bob now will be, because Alice has two outcomes, so it will be probability of getting 0. I'm writing a probability of getting 0 because Alice can get both 0 and 1. So probability of getting 0, and then probability of getting bi provided that Alice gets 0. Okay, plus probability of getting 1 into into probability of bi getting bi provided that Alice gets 1. All right, why I'm writing it like this? Because Bob does not know what Alice's outcome was. This is the punchline. That's why I need a probabilistic sum. Okay, and this will make sure that I get the same distribution. Let's check that. All right, so then probability of getting 0 for Alice was half, and probability of getting pi provided 0 is nothing but 0 pi mod square plus, similarly probability of getting 1 was half, and then it would be 1 pi mod square. And you can see this line is same as this line. Okay, you can calculate the same steps similar to that, and using the completeness relation again, but you can show that this is half. So if Alice performs a measurement, the probability of getting I is half. If Alice does not perform a measurement, the probability of getting I is half for Bob. So the probability distribution for Bob does not change, and that's why they cannot do any communication instantaneously. All right, the probability distribution does not change for Bob if Alice performs any local measurement. All right, and this was the claim for no signal learning principle, and we have showed it in an explicit example. And the general proof is given in the lecture notes, so if you're really interested, then I encourage you to see that. And if you have any questions, please don't hesitate to ask us during the live discussions, or you can post it in the Google Classroom. All right, so thank you so much.